Last tournament. Guess you guys should be off the freezing here. So. Oh, go away.
The lights
yeah, we're good with the lights. The projector got fixed, so that one hasn't been working for 3 weeks, but we're good now. We're cruising. Cruising. Ooh. Ooh. 2 minutes.
Hey, Dr. D. Blake Whittingsley might be a little bit late. We just got out of a capstone meeting, so he might be like 2 minutes late. He's boarding over now. Hey, I'll let him know. I'll give him the response.
All right. Thanks for letting me know.
Of course.
Who's your guys' capstone advisor? I might have to have words.
Professor Tomford.
All right. No, that's it. She did it on purpose.
It was actually a secondary meeting after her meeting, so it was great. Worked well.
Oh. All right. Let's get going. It's 12:30. All right. Lord, thank you for bringing us together this afternoon. Pray that you help everybody's day go smooth, that you would help us to transition back on campus. Help us to stay focused. In your name we pray. Amen. All right. Here we go. All right. So, who's here? You know what, Taylor, today I would appreciate it. Oh, you don't have to pop out. So, all right. I need somebody to be the person that checks chat for me today because the chat in Zoom. So if somebody could please, Hannah, thank you for volunteering. If you would please sign into the Zoom meeting. Just so you guys know, it's not going to happen today, but in future classes, you are going to want to have your laptops up and open into Zoom in case you have to do breakout rooms with your groups because they're not all in class. About half of them are in the flip section, right? So just be aware. Okay. Cool. So what do we got? What do we got going on today? We're going to recap, and then we're talking about solenoids and electrostatic micro actuators. So what is all that? All right, so people are confused by electrical. It's quite a bit. It covers the entirety of last week and a whole 2 other classes that you guys took before getting to this point. So why don't we just break it down to the specifics? To do circuit problems in this class, you need to be comfortable with using Kirchhoff's laws, right? The voltage law and the current law, as well as the element equations, right? 2 of which are first order ordinary differential equations, and the other one is Ohm's law, right? So in order for us to do any circuit problem in this class, whether it is op amp or otherwise, we need to be able to do a Kirchhoff's voltage loop, Kirchhoff's current law, and write down what the elemental equations are, right? For this class specifically, we need to write all of our equations for circuits, not for op amps, just for regular circuits, in terms of IL, E sub C, or E in or I in. You don't want to, there's a reason for it. And the reason is going to be apparent once we get out of the modeling phase of class and into the analysis phase. And he keeps saying that, and I don't believe him. Well, it'll be okay. I promise, I'm not lying. What we're doing is we want everything in terms of either E sub C or I sub L, right? Because those are the 2 variables that are actually going to be most applicable, right? We want to know how much voltage are we dropping across our capacitor, how much current do we need to pump through our inductor, right? We showed last class when talking about motors that the current through an inductor is extremely important when developing a magnetic field, right? That is why we are interested in that. We're interested in the voltage drop across the capacitor because the capacitor is kind of like a tank, right? And it stores charge. And we need to know how much voltage we are dissipating by going across that element, right? And that's what's going on with that. For op amps, we do everything in terms of the input voltage and the output voltage. Why? Because physically, that's what we care about, right? We care how are we amplifying, how are we filtering, what is going on with our signal. We put it through the op amp, something happened, I want to know what happened. For particular problems that we're going to do today, one of them calls E out across a capacitor, right? That's because I pulled it from a different textbook than our textbook, right? And that textbook does it slightly differently than we do. Is it wrong? No, you can do these using whatever element equations you like, except that the way that we have it set up, we don't have to use the integral of 1 over C, right, as talking about our voltage. Right, so by using I is equal to C, E dot C, you don't have to put an integral into your equations. Everything is in terms of a derivative. And I think personally, it just looks a lot cleaner than having to write integrals every time that you want to write out these equations. Is it wrong or right? No, it's equivalent. It's the same thing. You will get the same result. It's just whether or not you want to use an integral or derivative. Okay. Electromechanical systems are the byproduct of when an electrical system and a mechanical system love each other very much. Okay, that's what happens. You get an electromechanical system. Still a good joke every single time. What we're doing with electromechanical systems is we are coupling an electrical system with a mechanical system, right? And so you can actually decouple them to do your models. You can write a model just for your electrical system and one just for your mechanical system. And in fact, I would highly recommend that you do it just like that. Don't try to combine your equations to get one master equation. It's going to get gross and sloppy. Leave it as a system of equations, right? It doesn't buy us anything at this point to combine them all. So leave them as separate systems of equations. The main reason is, and you'll see it with some of the electrical systems, right? You end up with equations that one has I sub L in it and one has I dot in it, right? So if I wanted to substitute one into the other, I'd have to take a derivative, right? Or even worse, I'd have to take an integral over an interval that I haven't given you to take it over. So it's an indefinite integral, so you have to make sure you carry your constants, right? We don't need to do that. We don't need to worry about that. When we get to Laplace transforms, all of that gets taken into account with the Laplace transform, and it becomes much easier, right? Essentially, you will be able to solve ordinary differential equations with algebra at that point. You don't have to do any of the ordinary stuff. You can just use algebra when we get to Laplace transforms, right? So don't try to do all of the legwork before you get there, right? Because it's going to be easier for us if you have two separate equations that we can just use algebra to combine later instead of having to do integrals and derivatives. Okay. All right, that's probably a little bit more than we were hoping for. Tesla heresy, it's true. So I just want to say this, right? And Taylor, I did see your comment, right? And they don't talk about those things. The one in Discord about the superchargers. Oh, okay. He doesn't even remember. Well, you know what? Dr. D remembers. Okay. They don't talk about a lot of things. And also, I definitely don't think that the IC engine will be obsolete in the next 5 years. It's not going to happen, right? But so I don't want you to think that Dr. D is a huge proponent of electric cars. I'm neither pro or neither for nor against electric cars. I am very agnostic on electric cars. They are fine. I'm not going to spend the amount of money on one that they cost right now. It's just not going to happen. I mean, there's new Xboxes coming out, so you have to prioritize. Kids need diapers, things like that. All right, but yes, I agree that was sort of a propaganda video. And when I went to post it on YouTube, it also violated some copyright infringement stuff, so I had to scrub it from the video anyway. So you won't be seeing that again if you watch the lecture later. All right, so there's that. Do you guys have any other questions before we move on to doing some example problems and then talking about solenoids and MEMS, essentially? What we got? Oh. I thought I saw something in the chat, but then we'll talk about that in a second. But yes, there is an exam next week on Thursday. We'll talk about that in a second. In fact, right now. Why don't we talk about that right now? All right, so you guys did homework 1, you did the ethics paper, right? And now what's left, right? We've got homework 2 due on Sunday. Take a look at it, start it sooner rather than later. We've got exam 1 next week on Thursday. And then homework 3 due a week from Sunday. I will post homework 3 when I get back to my office today, so you guys have it. I don't expect anybody will be able to do it just yet, but we will start getting into the homework 3 stuff next class. We're going to jump into fluid systems next class. So, I guess be excited about that. I don't know for you guys if that went from bad to worse, from electrical to fluids or what. But it's fine. It's going to be fun. It's going to be fun. So the exam, what's on the exam? Everything up through homework 3. So anything up until next class on Tuesday is exam eligible. So it's all modeling stuff. You're not going to, obviously not going to be asked anything about analyzing systems because we haven't done anything analyzing systems. You are going to have to set up potentially mechanical, electrical, electromechanical, thermal or fluid models of systems. Now remember, you have a fixed amount of time and these problems do take a certain amount of time. So I'm not going to give you more problems than it takes to do in 2.5 hours. The way it's going to work is you guys don't have to come into class that day. We'll do it all. Well, half of you guys wouldn't be here anyway. But to keep it fair and feel like everybody's on a level playing field, the people who are normally in class will just stay home that day. You guys will all take it at the time that class is. It will become available on LoudCloud. You then will have 2.5 hours to complete the exam plus 30 minutes beyond that to scan it and get it back. Okay. Once the Dropbox deadline closes, that's that, right? So make sure you guys give yourself enough time. While you're taking the exam, you're going to be on a Zoom meeting anyway with me. I'll be sitting, like, in case you have questions or anything, right? You can ping me. But you're all going to be in a Zoom meeting, and I'm going to have you guys join with your computer, but also with a secondary device that is a camera showing your workspace, right? So it doesn't show your exam, doesn't have to like get up on your exam. That's not what we're doing. What I want to be able to see the area that you're working to make sure it's clear of other things, right? Those of you who had me before, some of you had me last spring when we did this, and it worked out pretty well. It's pretty simple. So yeah, you'll have your camera on you, right, from your laptop, and then you'll have your phone or whatever, iPad, whatever you want. Make sure it's plugged in, right, pointing at your work area just to make sure there's no extra stuff in it, right? If you have questions about whether or not you want to test your setup, that's fine too. You can join office hours, get with me on Zoom, whatever, and I can tell you if it looks fine or not if you want, all right? Okay. People at home, am I being loud enough for you guys to hear me? Okay, I have to check all the time because last class I had some complaints. And honestly, it's getting kind of hard to be really loud for like 5 hours straight. So I'm just gonna throw that out there. All right, you guys have any questions, comments, anything right now? Remember, I've got office hours after class, right? So give me a couple minutes to pack it up and get up there, and then you can zoom in because even though you're here, faculty offices are magical. It's the demilitarized zone. Okay, nobody's allowed in there. All right, you guys got any questions? You okay? No. All right, well, if that's the case, why don't we start with this problem? This one looks super fun. Jeremy, it says on my magic sheet of paper that I put in the announcements for everybody, so everybody should have it, that you can do this problem. That's what it says, that you have tried this problem. Yeah, what's up?
Do you want me to just raise my hand?
Sure. I mean, I didn't even see that one come in.
Someone said, did you say that iPads were acceptable to take an exam despite?
Like as a way of showing your workspace? Yes, it's fine. I wouldn't suggest taking the exam on an iPad though. It just doesn't seem like, I mean, pen and paper is probably your best. Oh, so I've also noticed this. I've graded enough of the things at this point to know that you guys have the same, apparently the students haven't informed the professors that there is some sort of a post-apocalyptic paper shortage in the world, because a lot of you guys just are trying to cram all of your work into like tiny corners of paper. Okay, please don't do that. Write big. Use. Okay. Nice, thank you, Jeremy. That is a picture. It's correct. So yes, try to do yourself a favor, right? Make sure that your work is legible, right? Make sure check your scans before you upload them so that you make sure that people can read them. It's not a huge thing for anybody, but just please make sure. Also, I gave you guys feedback on your homeworks, right? So if you look in the comments box, it's broken down by each of the questions. Yeah, Tom.
What was the title of the sheet where you see what place where all those?
Yeah. And we're probably not going to get through all of them.
There's number 7 on week 3, number 8 on week 3.
So we're not going in order on the sheet though either. So I'm jumping around. I have to keep you guys on your toes. You can't so you can't fall into a pattern. Just assume that we're not going to get to the ones in the back. Okay, Jeremy, what we got going on here? Jeremy, I think you might be on mute.
What I was able to decipher so far was just the in and the outs, and then the picture. Then that's as far as I got, really.
So let me ask you a question here. So this is the one I was talking about earlier, right? So what should our dynamic variables be for outputs for electrical circuits? Correct. EC on IL, right? So the fact that this is EO is not wrong, right? Because that E out describes the voltage across my capacitor. But you also need to talk about the current in the inductor, all right? All right. Okay. So with the picture, let's talk about the picture. I'm going to talk about this picture. So with, that's what it was. With, hold on. I'm going to add something to the slides here really quick. No, come on. You can do it. There we go. All right. So with this, how many diagrams should we have for something like this? To get the complete model of the system, what do you guys think? How should we draw this to get the complete model?
Draw a diagram of it at switch 1, draw another diagram at switch 2.
Exactly, right? You want to complete the circuit using switch 1 and complete the circuit using switch 2. Now, when you look at this, right, what does that mean for us, right? Over here. What does that mean for us, right? So I've got my two, so I'm going to move this down. Yeah, you can see that now, right? So we're going to assume that this is in the switch 1 configuration, right? If this is in switch 1, then all of this stuff goes away, right? We don't worry about that. That doesn't do anything. If we're in switch 2 configuration, this is gone. The input is gone. Right? Okay. What do we have, right? Because it's not just enough to leave this, right? Well, we've got some current here. I've got a node here. I'm going to have I sub R coming out and I sub C going down. I've also got a few choices here for voltage loops, right? I've got the big one, I've got this one, and I've got the whole circuit as well, the whole perimeter, right? Call this one left-hand side. I'll call this one left-hand side 1 and right-hand side 1. Similarly, right, I can draw this, right? In this case, left-hand side 2 and right-hand side 2. Now remember, it's not just enough to just point at the figure on, like, when you get your exam, right? You have, say that there's an electrical system there, right? It's not enough to just say that's my picture and move on. Make sure you annotate it with the things that are important for your analysis, right? The picture is there, the diagram is there to help us. Right? It's there to help us figure out what all we need to go into our equations, right? So I might not use all of these loops, but now I will remember that they are there for use. Right? How many energy storage elements do I have in this equation? 2, right? I've got an inductor and I have a capacitor. Each one of those will contribute a first order ordinary differential equation to my model, right? I want to make sure that I have one equation for each energy storage element. What does that mean? I need to have one equation in terms of I dot L and one in terms of E dot C for this. Every capacitor and every inductor that you have needs to have its own differential equation to describe it, right? Because that's how we're getting the order of this system up, right? Because this is a second order system, right? We've got 2 first order differential equations that describe it in each configuration. What is this thing doing, right? Well, when it's in the 1 position, what's it doing? It's charging that capacitor, right? You're storing energy in the inductor and in the capacitor. Remember that video we watched on inductors last week, where they had the lamp that was running, and then when you turned it off, it still ran the lamp because, well, it stopped running the lamp for a second because the inductor started to charge, and then once you turn it off, the inductor powers the circuit. Same general principle here, right? Switch 1, I'm storing the energy, then I will turn it off and discharge that energy, right? Notice the only thing that changes between the 2 configurations is that you're cutting out the source in the second one. Everything else is the same, right? Everything else in there is the same. You're just cutting out the source. Okay. Yeah, Blake.
Does it mean that there are different ins and outs for both these portions?
So we're going to have to write ins and outs for them, and yeah, they're probably going to be different. We'll talk about that in a second. Good question. You guys have any questions on the diagram in general? What's expected, right? You really help yourselves, right, with this. Write down all the things that you know you're probably going to need currents. You know if there's loops, you should just don't forget them, right? Like, you might not use all the information that's on there, but it's helpful. It's helpful to not forget it, right? Let's talk about switch 1. When I say switch 1, I mean the circuit when the switch is in position 1, right? Some people will call it position 1, whatever. But here's the other thing. So this idea of switching, right? It's not unique to electrical systems, right? Think of each switch position as a state, right? Either I'm in this state or I'm in this state, right? You can treat mechanical systems in very similar ways, right? You can break the motion of, say, like a ball, right? Soccer ball. I kick the ball, right? That's the first part of it, my model. Then it's rolling. The rolling of it is the second part because there's no applied force anymore. The third part is the catching of the ball with the foot, right? Because now you're accepting that pass and you're absorbing some of that force, right? And so think of it, this is the idea here is that you can segment your model into different, I guess, different time portions, right? Different moments in time. At some point, this switch will be on. At some point, it will be off, right? You can model each case independently and still get the entire picture, right? And you still get the entire picture. All right, So what are my inputs here, right? What do you guys think? Heard it. EN, right? What's my output? Well, what are my outputs?
EC and IL.
Yep, EC and IL. And here's the tricky part. What about switch 2?
EC
For which?
for the input.
You can go with EC. Turns out that it's both. Why? Because you have stored something in there. You have what you have. That is your input. What are you going to get out? It depends on how long you look. I mean, it's going to go to 0 at some point, right? But your output is still EC and IL. Okay. The input and the input here is wonky, right? Because it's really, well, it's not wonky. It's whatever you have as your output for switch 1, right? Because that's what you're storing, right? It's just that the output is the same, right? The output's the same. And there's nothing wrong with that, right? You can have a system, mechanical system, where I put in a position and I get out a position, right? It's completely fine. Completely fine. Okay. What about mathematical truths? Well, if we're looking at this, right, what should our mathematical truths be? Somebody hit me with an electrical circuit mathematical truth.
Sum of the currents into a node are equal to the sum of the currents out of a node. So Kirchhoff's current law. You got the voltage law too.
I'm going to write it this way. IL is equal to IC plus IR. All right, I'll write it that way. Okay. So yes, and Olivia got us the IC equation. What else do we have in here?
EL equals L I dot L.
Yes, EL is L I dot L. Is there anything else?
Kirchhoff's voltage law.
Yep, yep. We've got a few of those.
ER equals IR.
Yep, and ER was R, right, Ohm's law. All right, so we've got Ohm's law, and I haven't written the voltage laws, but you guys are right? Let's talk about this, right? Which voltage law should we use here, right? Because we've got 3. We've got 3 to choose from, right? I've got the left-hand side, I've got the right-hand side, and I've got the total outer perimeter loop, right? Which one of these should I use? General rule of thumb. Right? General rule of thumb. Use the one that couples your energy storages. Use the one that couples your energy storages. Why? Because look what's going to happen. All right. Well, this not only couples your energy storages on the left-hand side, but it also brings E in, right? If you use the right-hand side, you have nothing that tells you how the input affects the output. You have only things that are in terms of the output, right? We need to understand how the input affects the circuit, right? Because otherwise, what is the point, right? There's no cause and effect. We have effect and effect. Doesn't make sense. So the way that we get the input in here, and you can see that the input is then coupled to both the capacitor and the inductor, is by using the left-hand side. If we use the right-hand side, we couple the resistor to the capacitor, which isn't particularly helpful. But I'm going to do it anyway, because I want to prove a point. And this is my point. What is the voltage drop across the resistor?
It's equal to the voltage drop across the capacitor, right?
Yes, it is equal to the voltage drop across the capacitor, right? And I'm going to prove it using KVL right now. But Noah, yes, it would not be wrong. Okay, so I said yes, but I meant no, it would not be wrong. Yes, that would be fine. So no, it would not be wrong to write all of them if you wanted to. If you wanted to. Okay. So for switch one, right? So far, right? I want you guys to notice this. So far, these equations right here, doesn't matter if I'm in switch one or switch two. Those are going to be the same. That node is always there. We always have the resistor. We always have the inductor. And we always have the capacitor. Those will stay the same regardless. For switch one, right? Let me do this right-hand side one first, right? Turns out right-hand side 1 and 2 are the same, right? Oh. It's a great time for you to test that. This is the test of the emergency alert system. Acknowledge. Acknowledge. I hit the button. Do I not hit the button? There we go. Apparently you hit the button there, but not in the middle. It's fine. All right, anyway. Perfect time for a test. Test of the emergency alert system. There is a meteor hurtling towards campus. Everybody duck under the desks. All right. KVL for the right-hand side is the same, regardless of the configuration of the switch, right? It's always going to be that loop between R and C. All right, so what happens? Well, let's go back and look at it for a second. Let's go back and look at it. If I'm running my loop this way, right? I've got negative ER plus E sub C is equal to 0, right? Because I'm bringing the current up across it from negative to positive. So that's going to make it positive. That's going to make this a source over here. So KVL 1 and 2 for the right-hand side tells me this, right? That's what it tells me. That's what we just said, right? Because they're in parallel and there's nothing else there, the voltage drops across both of those are equivalent, right? And so that's fine. And that's going to be something that we can use later. Let's use left-hand side 1. What do we have? We have En minus El minus EC is equal to 0, right? What about the KVL for left-hand side 2? There it is. Negative EL equals EC, right? Notice it is the exact same as the left-hand side 1, except we have removed En, which is exactly what shutting off that part of the switch does. We're just removing En, right? It's the same exact equation. Some sort of powwow up there. Let's sell tickets next time. All right. Is everybody okay with mathematical truths here? I typically, personally, I don't write that right-hand side because to me, I see that and I know, right? This just proves what we know, that the voltage drop across those two elements in parallel are equivalent, right? But if you forget that, you can always do this to prove it, right? You can always do this. That's fine. All right. Everybody okay with these? Do we have any questions on how we develop the mathematical truths for this particular circuit?
I have a quick question, actually. This is small, but for EL and EC, you made them negative, but we're going clockwise through the loop, right? And I feel like this should just be positive because we're going from the positive side to the negative side. Or is it negative because it's dropping in voltage? Like, what's the convention for that? Or do we just make it up?
Trevor, for this one right here?
Yeah.
So let's go back to the, right, so we're up here, right?
Right.
En is going to be positive because I'm going from negative to positive.
Right.
Positive to negative and positive to negative. So these are drops, right?
Okay.
Another way of thinking about it is once you hit ground, you should be at 0, right?
Okay.
So technically, and it's not drawn here, but technically all of these are thought to go to ground at the bottom, right? And so when you get to ground, you should be at 0. That's where you should be. All right. Noah, it doesn't really matter to me. I'm going to be quite honest. It doesn't really matter. You don't draw ground. You will notice that I didn't draw ground on there. It's assumed that it's at ground. If it's not, if it's someplace that else that's supposed to be specifically ground, you'll know, right? But for general circuit analysis, we can assume that we will be going to ground. Okay? You don't need to worry about drawing it. Would make things really weird if we didn't go to ground though. Like really weird. You have remnant material. All right, so how do we reduce this equation, right? So sticking with our theme, we'll keep with switch 1 first. So what do we have for switch 1? All right, we can start either with KCL or KVL to the left-hand side. Which one do you guys want to start with? Well, let's choose.
KVL.
Oh, it's too late. I got a KCL. All right, it's too bad. You guys can perhaps fight to the death. I don't know. Probably save that for something bigger though. There we are, right? So we got KCL. Great. But we need it in terms of IL, EC, and E in, right? Okay. Well, we already have this in terms of IL, done. This is going to be R, IR. Okay. Sorry, that's, Dr. D was kidding. E sub R over R. That's what I meant, right? Because IR would be E sub R. Ohm's law. This is my cross multiplying thing. Also, speaking of cross multiplying, for those of you who know Professor Higgins, if you go up to her and talk about cross multiplication, it triggers her like 100%. That's like a big thing for her. Don't mention it in her business. I'm not kidding. Anyway, see you guys. All right, so we're almost there, right? And the whole point of us doing and talking about KVL for the right-hand side was that ER is equal to EC, right? That's it. It's done. It is in terms of my dynamic variables. Notice there's no input, but that's fine because this is coupled together. And the next equation that we do will show us how it's coupled.
Why is it E sub R over R for IL? Oh, I see. Never mind. I got it.
Okay. Everybody all right with this? Is there any questions so far? Let's tie up switch 1. Okay. So we use this, now we use our KVL. KVL, so just so we remember, this one is from KCL. This is going to be from KVL left-hand side 1, which tells us that EN is equal to EL plus EC. Right? So the total amount of voltage in drops completely by the time we get to this. We need this in terms of IL and EC, right? Well, guess what? Theme. Total model for switch 1 complete. Well, you guys copy that down. I want you to think about this. What is the major difference between switching between position 1 and position 2? How does that affect the circuit? Exactly. Position 1 has an input. Position 2, that voltage source is gone. So, gut feeling, what do you think the model should look like for switch 2? Exactly. It's the model from switch 1, but the input is 0. EM is 0 because it doesn't exist. That's it. We can run through it, right? That KCL is not going to change. That's state for state 2, right? When the switch moves to position 2, the KCL stays the same. So that'll still be equation 1. But if we run our KVL, right? So let me label this so that it's not confusing. Don't want to call it state. I want to call it switch 2 from KVL left-hand side to right? The only thing that changed. So you can make an intuitive. We can use our intuition, right? We can use a direct substitution based on the differences in the model, right? To figure out how the model change. Now, obviously, this doesn't apply if by flipping that switch you then go to an auxiliary circuit that has yet another capacitor, inductor, and resistor, right? But for this particular circuit, the only difference is that when you flip the switch, you lose your input. So, I think on the PCL, yep. So let's do this. Right. So the red one's being for switch 2, right? We'll have the same KCL model, What is this? So I want you to see this too, right? If we really wanted to. Because I have this in terms of I sub L already, but it's already solved for IL. I could take the derivative of that and plug it in right here, right here. Okay. You could. If you did that though, you're gonna have to take an integral to get rid of the E dot there. Right, but watch what happens, right? If I take the derivative of that top one, notice what happens. I end up with a second order differential equation, right? I get C E double dot C plus 1 over R E dot C. And I plug that in for I dot L. And so I then get a nice, so it's a second order system, right? I've got 2 first order coupled differential equations that will produce a second order differential equation. Yeah, I would just leave it like this right here. I don't combine it unless you're told specifically to combine. The reason is that this one's not that bad to do, but some of them get pretty gnarly pretty quick, right? It's not that I don't think that you guys could do the integration or derivatives differentiation, right? But I don't feel like it's value added, especially when the whole goal is, like I said earlier, we're going to take this little Laplace transforms and then not do any hardcore differential equations anymore. Or maybe we're more hardcore because we've simplified it so much, right? And that's the way to think about it. masters of mathematics. And you walk into a math department, you just laugh at them. You walk away. The views of Michael DeGoria are not the views of GCU engineering. Anyway, you guys have any questions on this? Doing all right? Yeah. Okay. So let's do this one. This one looks super fun. Sean Stouffer. They had, I mean, I don't know why they had to put the only two people in any of my classes that have the same name in the same in-person section. I feel like it's they're really asking a lot of me. Oh, that's true. That could have been so much worse. Yeah. So what we got, Sean?
So you got to start with the diagram, the line diagram.
Sure. What's the best way to do this? Yeah, actually. There should be a marker floating around somewhere. Perfect. Yeah. So you can use the whiteboard and we'll take a look. Because while you're doing that, what were the inputs and the outputs for this one while you're gone? Mhm. Okay. All right. Sounds good. So if you guys can hear, because my microphone is not the best and it's far away. He had for the mechanical system, the electromagnetic force is the input and X is the output, and the input voltage on the circuit, and you said the current as the output, right? Turns out, as we hopefully remember from Thursday's class, right? Hopefully you remember, the electromagnetic force is actually a function of the current, right? Remember, the more current you put through that inductor, the larger the field is going to become, right? The larger the field is, the more force will generate, right?
I have a question.
Yes.
For when we're setting up like diagrams like this, do we need to do like a coordinate system for the electrical ones or just for the mechanical ones because nothing's going to be moving for the electrical ones?
Good question, Jeff. So for things like this, coordinate system in electrical is just you basically showing which way your current's moving, right? That's electrical systems are set up in such a way that we always assume that we go from positive and negative across our elements, and that is negative to positive across our sources, right? So if you look at this in particular, do it on here. And so if we look here, all right, this is always assumed, right? Specifically for our current law. Because why? Because if our current is traveling in this direction, right, in this clockwise direction, then this is a gain here, and these are drops, right? So we always assume that we have it hooked up like that. Awesome. So the thing is, you could get this, there's two things. You could say that the electromagnetic force is both the input and the output, if you really wanted to, right? Because that is just a function of that inductor thing, all right? So that's the thing to remember, right? So the electromagnetic force is what, right? We came up with an equation for it. It's B times L times I. It's the field strength times the length of wire times the current. And that's what it is. So, right, those two things are constant. Really, the only thing that's changing is that current. So, saying that it's the electromagnetic force is fine. You're just saying, in essence, that the current is really is your input and your output, right? It's just multiplying. It's just scaling the current. That's not gonna work. That's certainly not gonna work. So Sean has handed me a whiteboard. All right, let's see. The people in class can see it. Hopefully you guys will see this. Start this. Is this gonna work today? Oh. There we go. Yeah, that's fine. See this? No? Okay. All right, we've got our electromagnetic force, right? Spring force, damper, looks good. Yep. PBL. Right. You guys see this? I'm gonna draw it on the board on this. What else? All right, so you notice that Sean did this with inputs and outputs separated for each system half, right? Which is good. Good and it's fine. And you don't have to like worry that you did it wrong that way. You can also do this in terms of global inputs and outputs, right? Globals would be the output will be X and the input will be EN, right? I give some voltage and I get a positional change. Right? That is globally what's happening. All right. This looks looking good. Right? Steps through the truths and everything. So let's I'm gonna leave that up behind me. And we'll step through it anyway. All right, so here, right? Same free body diagram and electrical system model, right? The one thing that was said in the diagram that we didn't really address is that isobar is a function of our magnetic flux. And what is that telling us? Well, what that's telling us is that the book that I pulled this particular problem from wants us to change the dynamic variable that we've done to magnetic flux. And we can do that, but it's my personal opinion that as mechanical and biomedical engineers, the amount of times that you're going to care about controlling the magnetic flux of something is this many. So we'll do it as a mathematical exercise, but I'd rather that you can get down to this, right? That's fine. So we'll talk about it when we get to the end, and it's just a substitution of variables, kind of like when we talk about position, using velocity instead of position, right? We don't want to use x double dot, we use v dot. It's the same basic idea. We'll talk about it when we get there. All right. So we've got EN, FEM, and X. And I'm going to put green under these because these are my global input and output. So it matters. It doesn't matter right now. It's going to matter when we start talking about transfer functions. Okay? That's when it will matter. But today, if you have it set up as reducing two separate models, right, and you did inputs and outputs for each, that's perfect. Right? That will work. That will play every time. Okay? Remember, the electromagnetic force is a function of I sub L. Right, and it's just scaling it by two constants, B and L, L being the length of wire. All right. So let's start with the circuit. Right? So my mathematical truths for the circuit are S of L. I'm going to write this here. E sub L is equal to lambda dot. E sub L is equal to lambda dot. Because remember, right, this is going to play back later. Right? This is going to play back later, and we'll talk about it later. But remember, this definition was given to us last week on Tuesday, when we talked about inductors as elements, right? And we derived the voltage drop as the change in the magnetic flux, right? That's where we derive the voltage drop from. Okay, so just keep that in mind. What else do we have in this? That should be good. We've got a KVL here, right? That's going to be EN minus ER minus EL is equal to 0. Right, and that's basically everything we need to reduce the electrical portion of this model, right? Because this is what we'll do. So KVL said that EN is equal to ER plus EL, right? So EN, well, ER was just RIL, not R, no, yes. RR plus L I dot L. Hey, look at that. Done. It's our input and our output together in the same equation, right? That's it. The first order differential equation based off of my inductance. All right, remember, I told you, we know that lambda dot is equal to L I dot L. Right? Therefore, lambda is equal to L I sub L. Right? Those were given to us the last time. Cool. Okay. So that means that I dot L. Right? So now, if I wanted to change my dynamic variables, right? I dot L is equal to lambda dot over L. And I sub L is equal to lambda over L. Right? So by changing my dynamic variable here, I'm going to rewrite it like this. We'll get L over L lambda dot plus R over L lambda is equal to En or lambda dot plus R over L lambda is equal to E. Okay. So yeah, we're just using this expression we put on the top. We're algebraing it, right? We're rearranging it, getting it in terms of the things that we need, and we can write our model in terms of lambda, right? If we want. Again, I don't see the realistic point for mechanical or biomeds to do that ever. But, you know, we can do it. But we can do it. All right, is everybody cool with the electrical side, right? Is everybody okay with the electrical side? Cruising. All right, well, talk about the mechanical model. Well, it's a linear, it's not a rotational model, it's a translational model. Some of the forces is mx double dot. Right. And we're gonna have that. The reason that we're gonna have that is so that I can change my dynamic variables at the end. But if you just left it as FEM, that's not a huge thing. However, I will say that we should get in the habit of breaking this down to the current, because when we get to Laplace transforms, and I know I bring this up, I feel like I'm bringing this up quite a bit this year already. But when we get to the point where we're trying to combine equations, we need to have that in terms of offset, right? So if we get in the habit of doing it now, when we have to, when we need it, we won't forget to do it. Right? Okay. That should be all of them. So we should be able to sum our forces, right, and take care of that. So I sum my forces, right? Summing my forces will give me the electromagnetic force minus my damping force minus my spring force equal to mx double dot. And plug things in here. That's going to be B times L. I sub L is equal to mx double dot plus bx dot plus kx. Right, and feel free to leave it there as equation 2. But again, if you needed to change the dynamic variables, we can use I sub L, right, and get B L over L lambda is equal to M x double dot B x dot plus K x, right, or B times lambda equal to MX double dot plus lowercase b dot x, BX dot plus K. There we go. Change of dynamic variables. Yeah. So what we did was, because we have this written like that, we just plug in. Stop. What's the point of changing the dynamic variable? The point of changing the dynamic variable is if there is some particular, so normally the point is you can reduce the order of the system by doing it. Like when we do it for torque equations, when we do it in terms of omega instead of theta, right? In this particular example, the benefit would be that you want to know something about the magnetic flux for some reason. Typically, that's more of an electrical engineering thing. As a mechanical or biomedical engineer, right, you're less concerned about magnetic flux and more concerned about how much current do I need and how much, how much position or velocity am I getting out of it, right? So for this particular example, the point is mathematical exercise. But in general, changing the dynamic variable can be helpful if you want a specific response of something other than position or velocity or acceleration. Right? So it has the downside of not doing analysis as we go, right, is that you guys get all of the lead up, but we haven't done anything with it yet, right? I'm hoping that once we get into that stuff, we'll start seeing the utility of how we've been setting up the equations. Right? That's the hope. You guys have any questions on this? Changing dynamic variable notwithstanding. Good. The people at home. I mean, this is probably like the most exciting game show that you guys have ever been on, right? Other than all the other classes that you're taking in the same room. Yeah. If this was a real game show, this would be pretty boring, right? So you can say it's fun. Anyway. All right, cool. Well, that's that. If there's no other questions, let's talk about solenoid actuators. And so we're going to spend the rest of the class talking about different actuator types and how we can use them and how we model them. Okay? All right, so question number one. What is a solenoid? What is it? What is it? It's that. It is that. It's true. Well, what is it, right? It's a device that converts electrical energy into mechanical energy. Right, so wait a second. Did he just repeat the definition for an electromechanical device? Yes, it's an electromechanical device. But what is it supposed to do, right? Like physically. So close, Connor. At its simplest, it's a coil that's got three iron. That sounds a lot like a motor, doesn't it? At its simplest, a motor is comprised of an iron core that's got a bunch of wire wrapped around it, right? We call that an armature too. Okay. So how does it work? Well, electricity and magnetism, right? Sorcery and the dark arts. Specifically, we use the same principles that we use when we're talking about DC movement. So we energize our coil. This creates some magnetic field. The magnetic field moves the piece of iron through it. Right, when we turn it off, if there's no spring, then the piece of metal doesn't move anymore. So how's it different than a motor? How would you guys say a solenoid is different than a motor? There it is. That's it. Translational instead of rotational. It is the translational version of the motor, right? So it induces some translation, right? Perfect. So where do we use solenoids? What are some typical applications? Valves. Valves is the most common for sure. What else? You guys have any ideas? What is something that you can do? What was that?
Locks.
Locks. There it is. Yeah. A lot of locking mechanisms are solenoids. Was that coil gun? I can neither confirm or deny that. But yes. Anyway. So locking mechanisms, robotic actuators, and valves. Right. So the three main ones. There's an interesting video on YouTube if you guys want to check it out. Somebody built themselves a remote locking mechanism using a rotary to linear actuator in their house. It's interesting. It's not the same as a solenoid. It would have been better if it was a solenoid because it would be faster. But you know, that's not here or there. It looks ugly and thin though because it's like a plastic box with a bunch of wires in it, so it needs to be cleaned up. So, but if you're interested, there's some pretty neat stuff out there. People building solenoid and solenoid type devices. And so here it is. Right here's our picture of our solenoid that we keep coming back to. So what I've got, right? I've got this solenoid. Right, it starts over here. Right, I energize my coils. Right, imagine that this is a lot of coils of wire, right? It's just very, if you cut one of these open, right, it looks like it's almost solid copper because there's some wires, right? Okay, there's some air gap here, right? Why? Because when I energize this plunger, needs to go somewhere. So if there's no air gap, it won't move. The air gap is there to ensure that we have enough room to open and close our valve. Notice in this position, right, this is our seated position because it's seated back here, seated here. In our seated position, this valve is considered to be closed, right? Why? Because this is where the fluid is flowing, right down there. So this will create an electromagnetic force. It will push everything this way, thereby allowing this to open from supply pressure down. The supply pressure will push the fluid down through the fluid flow valve, right? When it closes, notice there's some drain here so that any excess fluid has a place to go, right? In this schematic, it should be noted that it should be a 34 valve because there are actually gaps between the valve and the wall, right? There is a gap, right? It's not press fit, it's not locked in place, but it's a very small gap, right? So that we don't have a common linkage that would otherwise. Why have a valve? All right, so yeah. So we turn it on, it pushes everything to the right, compresses the spring. We turn it off, it stops pushing, the spring pushes off. Right, that's in general. Hotel locking mechanism, right? You put the card in, it doesn't work. Right? You do it again, it still doesn't work. Third time's the charm, right? Get the door to unlock, complete the circuit. Solenoid opens after a certain amount of time, it discharges, solenoid shuts. Here's another way of looking at it, right? Same words, different picture, right? Instead of the full-on schematic, this is more akin to where we derive our model from, right? So we have the actuator as a lumped mass, right? We have the mechanical side as a lumped mass. We have the plunger, right? We've got our coil of wire. Right? So that's kind of where we get our most. All right, so we're gonna walk through this one together. So I'm gonna give you guys the next couple minutes. I want you to draw your diagrams, all right? Just so you guys at home know, I caught some people in the last class. We had to have words. I called on them to show me their diagrams, and they didn't have any diagrams. And we've been working for like 10 minutes. So don't be like the people at home from last class. So, thank you. Is it? The diagram is, yes, but there is one difference that we will talk about. And I want you guys to think about this while we're going through it. My inductance is a function of the position, not constant. So how does this affect our system? Yeah, just the diagrams, Taylor, yes, are going to be 100%. You guys follow. So, since that's the case, do your inputs and outputs too. And then we'll jump into it doesn't, whatever you want to do, it doesn't matter. It's taking a couple minutes. Oh, forgot to do that. So you guys already have the diagram. Yeah. Okay. So inputs and outputs. When we get to the truths, this is where we're gonna have to think it through. So what do we have for inputs and outputs? At the end. So IL isn't changing with respect to X, right? The current is just the current. What is changing with respect to X is the amount of inductance, right? So think about it this way, right? An inductor is just a bunch of coils of wire, right? And the solenoid is the metal part that goes through it. If you have, what if, right? So you typically use iron, right? Iron will magnetize in a strong enough field, right? Won't be a permanent magnet, but it'll have its own magnetic field associated with it, right? Let's think about this way. If I had a coil of wire that I put around an actual magnet, right, and I turned on some current, I've now created an electromagnet, yes? Pretty strong one because I had one in the beginning. If I start to pull that out, what happens to the part where the magnet no longer is? How have you changed your magnetic field? You've made it smaller, right? So the part where there's no metal, if it's not magnetic, no longer contributes to the inductance. So your inductance is in fact changing as the core moves through the coil of wire. So if L is a function of X, it's going to change in some way, right? But the current will stay constant, right? Or the current will change with time. It's not going to change as a function of the position. But you will have, I mean, overall, right, we're going to have X, right? Globally, we'll have E into X. And then we'll have that current as our local input and output, right? Now here's the part that's tricky. Here's the part that's tricky. All right, you guys want to start on the circuit side or you guys want to start on the mechanical side? Circuit. All right. Here's the circuit. So my circuit truths, all right, what do we have? Hit me with some truths for a circuit. Okay. Single loop, right? So single loop with no nodes. Yeah, we should probably use KVL. People at home, what is a truth for a circuit? Olivia is crushing these truths. True, Crystal, it is. But for this, you know what? Actually, for this one, it actually is. It's going to be important. Okay, so there we are, right? Except, is this true? Here. This is L of X. And I said, but it's not. I got it. Right? That's not. It's not really true, right? So we're gonna erase that for a second. We're gonna say lambda, because we know it's lambda. We know it is. But what was lambda? Lambda was L of X. If I take the derivative of that, what if do you take the derivative? L is no longer constant. Both of those things vary with time. How do you take the derivative? Right. So this becomes L of x dt, right? Y L pi L. Okay. That looks pretty gross right now, right? But we're gonna do one more thing. I'm gonna use the product here. And I'm gonna,
one, the derivative of L squared over dt times L.
so, Isabel. Sorry. And this is L of x. Also. So use the chain rule. And I broke it up, right? Because I know that all of the function of x, right? And so let me just take the derivative of it with respect to x. And I can use the chain rule and say, well, that's now, if it was ddt, I can make it d dx times ddt, right? Or dx dt. Well, that surely is interesting. That surely is interesting. This is the time where I'm going to tell you that L of x is equal to L naught divided by 1 minus x over. Where did you get that equation from? Nobody ever told me that. There's this great thing. It's pretty new. It's called Google. You type in what is the equation for inductance as a function of position, and we'll give it to you. And that's what I did. Because for the most part, you're not going to use this, right? Because what's going to happen? You're going to end up with a nonlinear equation. All right, and so really what we're doing is we're handling this as a nonlinear equation. Later we will come back to it and we'll linearize it, right, and do all that good stuff so we can analyze it. But for right now, all right, so the first, if you're using the 5-step method for solving problems, like we have been doing, the first 4 steps of that, it doesn't matter if you're linear or not. The only time that it matters is when we're doing that analysis. Because all we're doing here is we're going to plug in variables, and we can have a nonlinear model. That's fine. We have to, there's a couple of things. We have to recognize that it's nonlinear, is the first one. And once we figure out that it's nonlinear, then we linearize it over a small range. Right? This is like we did in the pendulum model. A small angle approximation is a linearized pendulum model, right? Over a small angle, 5 degrees.
Dr. D, I think you forgot a term on the lambda dot equation. On the first term, I think the mean I. It's right after the chain rule.
Yes, thank you. Good catch. I did it on purpose. Yes. It's a bad joke. All right. Yes, I missed it. Totally on purpose. Totally. Fell right on my face. Totally on purpose. Okay, so this is kind of gross, but we could, if we wanted to, using this equation that we wrote at the top right, we could get the derivative of that x if we wanted to. I don't particularly want to, so I'm not going to. All right, so what are we going to do? I'm going to write this equation. Lambda dot is equal, and anytime we see this term, we circle it in red. Anytime we see this term, we're going to write L sub x times x dot, because dx dt is just x dot, and y sub L, plus L of x, I dot L. And we'll leave it like that. And we'll use that later. Right, because we know that lambda dot is equal to E sub L. Right, so this is equal to E sub L. So how are you supposed to know that you're supposed to do that, right? Well, the nice equation, Li dot L, comes from the fact that we have decided that we're using a lumped linearly time invariant model, right? And so because of that, we can say that L is constant. Right? It's the same reason why we say that K for spring constant is constant, even though we know it's not really. But in practice, we assume that it is, right? In reality, this is how inductance works, right? It's going to change as a function of the position of your piston, right? So the question that we need to answer becomes, how much does it change? And is it so much that we need to incorporate it in our model, right? And those are questions that we will answer later. Because once we get to it, we will take this model, this nonlinear model, we will plug it into Simulink, and we'll have Simulink solve it for us, and then we will compare that solution to our linearized model, and we will see how much better it is. Because let's be honest, and we know it's going to be better. It includes more information. But is it so much better that it doesn't make a difference? If you're off by 10%, is that a big deal? It depends on your application, right? If you're driving 70 miles an hour and you put your cruise control on, right? And you're told, well, that's good to plus or minus 10%. Well, 7 miles an hour, not that big of a deal, right? But, something that's really small scale, right? Like doling out diabetic medication or insulin, as it is called, through a pump automated, like an automated pump, missing by 10%, probably not sufficient, right? So depends on your application. So I'll give you the standard engineering answer, which is it depends, right? As long as you guys answer all questions with it depends, once you get out in the real world, you'll sound like real engineers. It's also the most frustrating answer, right? Because I know as students, when I was a student, you always want an absolute, right? And unfortunately, it's not real world. Right? Conditions matter. Conditions matter. All right. Is everybody kind of with me on this and sees where we're going? For this class, for success in this class, is it important that you understand how to derive this nonlinear model? Great question. Not really. Not really. No. I'm going to shoot you straight on this one. Not really. Honestly. Is it important to understand how we came up with this? Sure. The math of it, I don't think is terribly difficult. The issue, I think, comes from not knowing all the pieces of the puzzle, right? You didn't know that L of X is equal to that, right? You don't know. How are you supposed to find these things out? There's a reason why I think McGraw-Hill is jipping you guys, right? Because they charge, you don't have to pay that much for textbooks, but you only get them for you. I've saved all of my textbooks. I have, they're nice to have, in my opinion. But my point is this: if you know where to look for resources, right, that's very valuable. So you should know where to look things up, right? You need to know where these things are that you're going to need if you need them. And the attitude shouldn't just be, I don't know what this is, so I give up. It should be, I don't know where this is, I need to look. That's the general attitude. All right, I will stop pontificating for the day slightly. All right, now that everybody's in a good and happy mood, what do we do with this? We've got our circuit, we can model it, right? So let's write our KVL again, right? We had En was equal to EL plus ER, right? Well, this is En stays what it is. EL, well, that was just Lx x dot I sub L plus L of x Notice it's very similar. Right? It's very similar to our normal truth for an inductor, right? It just has a little bit extra. I don't know. This is L sub x, yeah. This is L of x. And just so we remember, right, this is where that comes from. And there it is, right? That's the electrical system equation. I'm going to rearrange it a little bit, though. I'm going to rearrange it a little bit. So I'll get L sub x dot, well, let's start over. I'll get L of x, I dot L, plus R, I sub L is equal to E in minus L sub x, x dot I sub L. I'll call that equation 1. All right. Let me ask you guys this. That last term with the x dot in it, does that look like anything else that we've talked about, specifically when concerning motors? Is there a term that we have when we talk about motors that relies on the angular velocity of said motor?
Back EMF?
Back EMF, there it is. So essentially, we've incorporated some back EMF into this, right? Think about it, right? We're moving our magnetic field, right? It's a little bit different, right? We're moving something that has a field through a coil of wire. So essentially, it's the same principle as moving a wire through a field, right? Instead of the field being constant in one position, we're moving the field instead of moving the wire, right? There's still some velocity of that wire relative to the field. Get another one of these. Let's talk about the mechanical system. Right? Is everybody okay with the electrical system? You guys have any questions? No? Again, right, like the point is that we can handle a nonlinear system, right? We can handle a nonlinear system. We're just not going to analyze a nonlinear. We can model it fine using steps 1 through 4 of the Dr. D super number 1 5-step circuit method to solve them all, right? But once we get to step 5, that's when we have to change our game. But modeling it, we should be able to handle nonlinearities, no problem. Okay. So what about this mechanical system? What about this mechanical system? All right, so if we sum our forces, we get, oh, did we not? We didn't do truths yet, did we? That's right. Sorry. Yep. Sum of forces, Newton's second law. We got Newton's second law. What else do we have? Yep. And that is where things get tricky. Because remember, we have to change that. not. So, all right, if you go back to your notes from Tuesday last week, the energy that is stored in an inductor, 1/2 Li squared, right? 1/2 Li squared. But isn't force just the change in energy with respect to position? Okay. All right. So for this, zeta is 1/2 L of x I sub L squared. So if I take the derivative of that with respect to x, I sub L doesn't change with respect to x. That's a constant. 1/2 doesn't change with it. We end up with FEM is equal to zeta dot, or not zeta dot, sorry, d zeta dx. Make sure that this says true. Is equal to 1/2 dl of x dx il. Oh, this guy again. L sub x. And there we have it. That is our electromagnetic. This is important, right? Because you want to use B times L times I, right? Where L is your length of wire and B is your magnetic flux density, right? Unfortunately, that is completely dependent on L, right? B is thought to be constant, right? But the amount of force that we're generating is really dependent on how the energy changes with respect to our position. And so here we are. We'll rewrite that. So now we've got everything we can write our reduction. All right, so if we sum our forces, I have FEM minus FB minus FK equal to MX double dot. Let me substitute some things in and rearrange. And there it is. Just so we remember, the electrical system looks like this. There's our complete model. We have one equation describing our electrical system and one describing our mechanical system. Leave them separated. Don't put them together. There's a big headache. So if you solve one of these for one of the other variables, it's gonna get hectic. It's not worth the headache, right? We'll learn how to handle it much nicer when we get to Laplace transforms. All right. So nonlinear system, right? What order is this? Is it second? The mechanical system is second. Yeah. So what happens when you have a second order system, a total system who has second order subsystem and a first order subsystem? What happens there? You're going to end up what we would find is if we put these together, we'd end up with a third order system. Okay. Cumulatively, this is a third order system. So I want you guys to think about order of systems in this way. However many equations I have, all of your orders stack, right? If you need two first order systems to talk about a model, then it's a second order system. The reason that this happens that way is because it's all about, and we'll see this when we go to Laplace transforms and we combine all of our big bad equations, right? You get like a fourth order model. Well, a fourth order model has four roots. Those are all going to tell you a little bit of something about what response that you should expect, right? And so it all comes back to what we learned in differential equations, how we can apply our knowledge of that. We're not going to do differential equations, right? But when we get to Laplace transforms, some of you will feel like I'm cheating when I come up with some of these answers. It's not cheating. It is using the knowledge that I've acquired by taking classes like differential equations, because I know what to expect my solution to look like. So I'm making my solution look like it's supposed to. It's not cheating. It's using the knowledge that you should already have to make a decision about how something should come out, right? You know how the differential equations are going to play out. First and second order systems are documented very well about what we should expect the solution form to look like, right? So when we get there, you're going to see, I call it black market math. There's going to be times where I multiply something by like 3 over 3. And people are going to be like, you can't do that. That's not, why would you do that? It doesn't make any sense. It's wrong. So, yeah, but it can change the way that a certain term looks so that it fits a certain form, so that I can then say, well, this is a sine wave that's coming out of here, not a step up. Right? So we'll talk more about that later. But overall, orders of systems matter. They tell us about what to expect for our system response, right? All right. You guys have any questions? No? All right. Well, if there's no question, and we'll just keep cruising. Where are we at? Oh, we got plenty of time. Talk about electrostatic microactivity. What is an electrostatic microactivity? What do you guys think? Based on the name, what do you think it is?
Is it like a solenoid, but using a capacitor instead of an inductor?
It's really close. Really close. It does use a capacitor instead of an inductor, but they are really small scale electromechanical devices that use electrostatics instead of electromagnetism. So they're so small that we don't have room for coils in electromagnetic induction. We're going to use electrostatics. So what does that mean for us, right? What does that mean for us? Well, since we're dealing with electrostatics, here's the example I want to use. Have you guys ever, combed your hair early in the morning? There's a bunch of static. So like right now in this time in Phoenix, when we have all the static, right? It's dry. You comb your hair and then you have the water running. So you put the comb next to the water and it bends the water. You guys ever done that? That's electrostatic, right? The force provided by an electrostatic charge, okay? So we're talking about really small amounts of force here, right? Which is why these things have to be so tiny to capitalize on that. So how does it work? Just talk about it. You're going to use electrostatic force. Electrical force of repulsion or attraction between charged particles. And that picture placement is perfect, right? But yes, I did say charged particles, and I understand that sounds like chemistry, right? And I know. Fine, don't worry about it. It'll be okay. What are some typical applications for MEMS? What are some things that we can do with micro actuators? Right? Well, think about this, right? These are small devices. So what are some applications that we would want to use a small actuator? What are some devices that we would want to use a small actuator? Somewhere. What kind of robotics? Like what kind of think, right? Like what?
Like I was thinking like, maybe, I know it's like, Michael Atwood, but I was thinking like, when it comes to like in the biomedical field, like, how like diagnosis and things, like, I don't know how, you know what I mean? I don't know.
So, all right, so I do, when I was at ASU, one of the professors that I tutored for, he was big into micro and nano fluidics. And he would do a lot of stuff with, it's MEMS type devices, but fluids devices that are super small scale. You can do like drug testing and other sorts of biological testing using very small scale fluidic channels and devices, right? And so something like that, sure, you could use, it would be a MEMS type device, but not really electromechanical in nature, right? That's more of a, it's more of a fluids, very fluids thing. But I see what, I know what you're going with. Not wrong, just slightly different application. But you are right. There are certainly biomedical applications for MEMS. And we've got surgical microgrippers, right? So like a Da Vinci robot uses really small microgrippers to hold things in place and perform microsurgery, right? Optical microscopes, really small cameras. When I was working at Picatinny Arsenal, there was a big push in the fuse division where I was working to incorporate MEMS safety and arming devices into fuses. Right? As you can imagine, these are really small, right? And so a very small amount of force is necessary to move it, right? So if you have a safety and arming device that requires a small amount of force, it's problematic because if you shake it the wrong way, you could arm an explosive and not mean it, right? So it's a really challenging problem. The other part is they are really small, right? So if you subject them to really high G loading, I don't know, velocities coming out of a gun barrel, it could break. Right? So how do you make something really small that's robust enough to high loadings so that it won't break and that it won't activate itself in that environment as well? Right? It's a really challenging problem. But this is it, right? Like electrical devices, technology is getting smaller and smaller, right? And MEMS is at the forefront of what's making that possible. Right? You've got MEMS accelerometers. Your iPhone uses a MEMS accelerometer. Sure. There's a lot of stuff out there. It's pretty neat. All right, so how does it work? Well, similarly to solenoid, and we're going to energize this. You can see our circuit is built here. And this is a microgripper, right? We've got one side that's grounded, that's not moving. And we're going to charge it up. As we charge that up, it creates an electrostatic force. That force pulls the drive on, pulls the closure on, right? So pulling this drive on, pulls the closure on, That's going to extend our spring. Once we turn it off, the spring and the damper move it back safe. Right? So we turn it on, it closes. We turn it off, it opens. Right? Great. And these are small scale devices, right? Another way of drawing this is this. Right? Sometimes these are called home drives because it kind of looks like a phone. Sometimes these are called home drives. So here we are. What time is it? Okay, we're good. We might even have time to do another problem after this. Crazy. All right. We want to create a mathematical model. This is the third before we have this is an RC system. Similar to our circuit, when you use a capacitor instead of. Notice, just like the last one, the capacitance changes as a function of the position. Right? So that's fun. Right? So that means what? That means that we're going to have to treat this in a similar fashion to what we did last time. And if you're thinking right off the bat, well, that means we're probably going to end up with a nonlinear model. Yeah, we'll probably end up with a nonlinear. So how do we do this, right? Well, I want you guys to take a couple minutes and draw your diagram. So no reason. Let's take a couple more minutes. All right. You guys good with diagrams? You want another couple minutes? All right. I guess nobody's asking for more time. So, Hannah, as your reward for manning the chat today, you may pick somebody who's not in class right now to show us their circuit diagram. All right, Zach, you can show us your circuit diagram, please. She apologized, but I don't know that I believe her based on how she said it. Just
I'm not gonna lie. I was trying to figure out how to do how to finish up the little nubby guy, and how to integrate him into it.
you mean the mechanical system?
That's the one.
What? All right. Well, show us what you got on the mechanical system then. How about that? We'll talk about it.
For the mechanical system, I just went and I just had a square. Sorry, it's hard to see with the background, but I just had a little square with like the spring pulling away with a spring force and a dampener force, and then the FES going in towards the electrical.
That's it. There you go. What do you need? Good stuff. All right. We still need a circuit diagram though, guys. So volunteers. Any volunteers? Preferably from the people who are being very quiet and are not in the classroom today. Hannah, you're gonna have to pick somebody else now. Edgar? All right, Edgar. See your circuit diagram, please.
I'm not sure if I did it correctly, but
We'll talk about it.
I just drew like, I don't know if you can, oh, wrong one.
Yep, right there. Good, perfect.
I drew like the IR, IC, and then that's as far as I got.
All right, cool. Well, that's looking good. My one comment would be that that IR, right? Remember the current there is constant, right?
Oh yeah.
It's all going to be the current that I see. We're going to describe it as I sub C. But good stuff. Good stuff. Thank you. Both guys. Thank you. All right, cool. So look. All right. I mean, basically a block, right? Stylized block. My drawing skills don't get much better than that, but you know, this one, I mean, it's pretty good. All right, same deal that you guys showed on the video. Thank you. Thank you, thank you. All right, so let's talk inputs and outputs. What do we got for inputs and what do we got for outputs? Okay. Yeah. So you can write it as FES, right? But remember, what's creating that electrostatic force? And we haven't talked about electrostatic force at all in class before, right? But what's creating it, right? It's the charging up of that capacitor is what's creating that. So that voltage drop across the capacitor is what is generating FES, okay? So again, FES is fine, right? But just remember, it is a function of E sub C, right? It is a function of E sub C. Okay, so let's talk truths. You guys want to do the mechanical side first or the circuit side? Circuit. I mean, you guys, for a bunch of people who complain about how they don't like circuits, you guys are always choosing the circuit side first. Right? What's that? Okay. All right. So circuit truths, right? I'll do the hard one. You guys give me the easy one. All right. All right. So all right. Say that one more time. What you got?
Q dot is equal to C sub X dot E sub C plus C of X, E dot C.
Yeah, man. That's it. Nailed it. All right. So what is Sean talking about? Right. Remember, this is similar to what we had to do for the inductor, right? But this time, instead of using flux, we're going to talk about charge because Q is equal to C of X times E sub C. Okay. Because remember, it's not constant. So when we take the derivative to get the current, we end up with dC of X dx dx dt E sub C plus C of X d E sub C dt, or we'll call this part Cx, right? Like we did before. This is X dot E sub C plus C of X E C dot. That is going to be I sub C. The one thing that we need, though, if we're going to do this, is we need to know what C of X, right? And we can look that up. It's this. It's this, obviously. It's obviously. Right? Everybody knows that. Well, that's N, not N, that's 8R. Times the emissivity times the area divided by distance. And we're just going to leave it there. We're not going to talk about it because we're not really going to use this equation. But just so we have it, right? For completeness. Okay. Yeah. Or SMC. All right, so we're good there. I'm going to put the mechanical truths down here in a minute. Well, let's just do them now. Let's do them now with him. So it's good to have, because if you were going to do an analysis, you need to know what it is. If you saw something like this on a test, then I would provide you with what C of X is. The number of times that I've used the equation is just 0. So I am not up on what's going on with MEMS, right? That's not my jam. To be clear, but being able to understand the underlying principles is what we're really going after. And so this class is less about me. It's not about me teaching you guys how to use MEMS, right? It's me teaching you guys how to model different types of circuits, and this happens to be one of them, right? It's just a really small RC circuit. And because it's so small, we have to take into account the electrostatic force. Now, overall, if we're going to see something like this on a homework, that's more reasonable for me to ask you to do something that's nonlinear, as opposed to an exam where I'm not letting you use a computer or anything outside of a calculator to figure out what's going on, right? Especially when we get to analysis. But if you did need to look at something like this, I would provide you with what the C of X would be, so you could do it. Sean, go.
The homework is in, when we're solving for you want us to write out the derivative state first, then the final one. So the truth, or if we just went I sub T equals Q dot equals C sub X X dot without the part of that.
You probably get full credits. I would. So the reason that I did it this way is because I want you guys to see it, number one, and number two, you're pretty much guaranteeing that you're going to write it down and not have any slip ups right when you do it. So I would recommend doing it all out. If you don't, remember, I can only grade what's on the paper, right? So if you happen to go C sub X and you write X dot, right, then unfortunately that becomes wrong without any recourse for me to know what you will do, right? So the more work you include, the better off you'll be in terms of getting picking up any partial credit along the way, right? Then I don't have to guess I don't have to try to get in your head, and it's all on the right? How you guys doing at home? Doing all right? Everybody good? Jeremy, you look pretty good. Leaning back, your head up. Look like you're screaming. You're screaming my name in anger in your home. All right, anyway. Mechanical system truths. What do we got going on?
I do see like a verbal, right?
Sure.
F sub PS 1 half C sub X C squared.
Got it. All right, so where does that come from, right? Again, if you use the previous problem that we did as a starting point, right? Remember, this is just the energy, the derivative of the energy with respect to position, right? Okay. Well, what was energy? When did we talk about that? On Tuesday last week, right? It's in your notes. So if I take the derivative of this with respect to position, right? So d zeta dx is equal to 1/2 c of x 60 squared, right? That guy, which we write that as cx. So FES is equal to 1/2 c sub x EC squared. We're also going to have damping and spring. And don't forget Newton, right? He was pretty good at math, from what I heard. Pretty good. He also makes really good cookies. So. All right, hang on. What time is it? All right, cool. We got a little time. So we can run through one more after this. We're about to tie a bow on this. Do you guys have any questions about this? We understand where FES comes from, right? So if you don't know what the electrostatic or electromagnetic force is, you can always derive it from the energy. If you don't know what the force is, right? If you're uncertain, you can always derive it if you know what the energy equation is in this way. Okay. Well, let's do our reduction, right? We'll start with the circuit because consistency, I suppose. So KVL tells us that En is equal to EC plus ER, right? Okay. So En is equal to EC plus 1 over R times, not 1 over, sorry, RIR. Oh my gosh. I apologize. But IR is just IC, right? R times IC. Yes, we came up with an expression for I sub C in terms of, right, so what is that? That was Cx x dot EC plus C of x E dot C. And look what happens if I rewrite that like this. Bracket. Okay, so I can do some algebra and rearrange some things. I'll call that 1. We'll call that 1. So we got that, right? What did we do? I don't remember. We just this is this. We derived that on the previous slide. Where did it come from? Well, it came from Q. We had to start with charge and work our way up to what the current was. Start with charge and work our way up to what the current was. Okay. So now, if I sum my forces, that, okay. So let's rewrite this and rearrange some of the things. FES is just 1/2 C sub x EC. Once again, we end up with a third order system, right? very similar to our solar light, but much smaller scale, right? Is there any questions? John?
You're raising the, put one on each side.
Yeah, so the reason that I did that was because just like in a motor, this X dot kind of acts like a back EMF. And so in terms, if we were looking at this in terms of a total voltage necessary, you would have to subtract, like you're, it's almost like the same idea as a friction, right? You have something fighting your system. So you need to have a little bit extra to actually get out or for your input to be as potent as you want it to be, right? Because there's something fighting it. So that's the only reason. It's also because the X dot comes from the mechanical side of the model, so it's kind of like it feeds back in from the mechanical side. And we'll see when we talk about it's not a linear graph, block diagrams, how to do our equations in block diagram format. You can see how you can see all your feedback loops playing with one another. And that's really helpful when you start doing Simulink models, because that's how Simulink is developed. It's all graphical with feedback loops in block diagrams. Any other questions? Well, I think we got like 10 minutes. Do we have enough time to do this problem? Connor, do we have enough time to do this problem? If we started,
I started, yeah. I like it.
go for it. This will be the last thing for class today, guys. All right. So while you're drawing up your guy, you inputs and outputs. What are you thinking? Yeah, you can draw while we talk.
Inputs, I was gonna say, FDS and C curve, and output video.
So remember, we're not going to do any of that VO business, right? So it is VS for sure is my input, or what we're going to call it EN. It doesn't matter. VS and EN are the same thing here. But you only have one energy storage, so your output is going to be in terms of E sub C, right? E sub C. Yeah. So we don't want the whole voltage drop there. We just want to write it in terms of, I mean, it's the same voltage drop. It doesn't really matter, right? They're in parallel. Okay.
But I did this whole thing.
Well, no, I mean, I'm doing it the same way. Right, it's just that the voltage drop in here is good across the capacitor, right? Okay. Just show me what you got. There's more than one way to do this, but just remember, we always want inputs and outputs that are dynamic variables, right? We want them to be E sub C or I sub L and E in or I. Those are the only, we're highly restricting this, right? And I think I said at the beginning of this class, but it might have been at the beginning of the other class, I don't remember, so I'm going to say it again. There are multiple ways to do these problems. There is a world in which you can use this truth. Hold on, I gotta unfreeze. There is a world in which instead of using this, people like to use this. There is a world where people like to use that. The integral, long received integral, ICT. It's gross. I don't like it, and we're not going to do it. Right, exactly. So, I mean, those are equivalent, right? You will get the same answer. It's fine. I just prefer to use the derivative as opposed to using the integral. Okay. Okay. So what? We have our, I'm going to read.
For the truth, I was looking at that node.
Mhm.
Said I1.
Yep.
And then, I actually had a question about this part, so how it goes to the other circuit on top, well, you know what I mean?
Yeah.
Oh, hey, yeah. There it is. So, I was, never mind, yeah, that's what I was.
Right. So that's what you got on that whiteboard there, for sure. I just renamed them. IR1, IC, and IR2. Do you need anything else to do this? Do you need to do a loop or anything like that? Here's the thing. I want you to look at this, right? These are terminals. Imagine that these don't exist here because they're making you think that there's extra circuit there, but it's not. That's just where I'm connecting my wires to get my readout. Really, I'm just putting the alligator clips here and here, right? And you're reading before and after that. Okay? These don't serve any purpose other than providing a place where I can make a read. Okay? So, do we need a KVL here, right? Well, I mean, I guess we could do one in here, but that's going to be trivial because it's just going to tell us that the voltage drop across one is equal to the voltage drop across the other. I mean, we could try to do one in here, but that looks like a pain in the butt. And actually, we don't need it. We actually don't need it. Because what we're going to do is, as Connor has written on that whiteboard, right? We have this. And this is everything that we need, right? Because of a special, very specific reason. I'm going to ask you, Connor, what is the voltage drop across ER or R1? What is the voltage drop across R1?
Would be EN minus EA. Or, right? One that goes.
And how much do we have going through that node? How much do we have left over? Right, because remember, the bottom is at ground, right? So how much are we going to drop across that basket?
Across all one.
So on the back end of, let me go back to the, so when we're here, right, we've got EN coming in. How much do we have over by A? We can call it EA if you want, right? How much do we drop going across this capacitor?
Drop I1 minus, or I1 minus R1. Right?
So the voltage drop across here is just E sub C, right?
Right.
So the voltage drop across here is E sub C, which is the same as the voltage drop from here to here, because the same potential, right? If you're 0 on the bottom, that means how much did you have left You have E sub C left. Right? Just think about this. I have to drop everything by the time I get back to ground, right? That's the way it works. Everything is gone. How is everything gone? Well, I know I dropped by E sub C there. And if I had 0 coming out, then that means I have to have E sub C coming in. Right? And so this problem, this is just E sub C, En minus E sub C is equal to R times IR, or you could rewrite IR1 is equal to 1 over R En minus EC, right? Now that's in terms of everything that we need. So we can reduce this, right? To reduce this, we say IR1 is equal to I sub C plus IR2. So ER1 over R1 is equal to C E dot C plus ER2 over R2. Right? We know we just went over that this is equivalent to that. This is here. And ER2 is just EC. So we can rewrite this entire thing. And that's what we're doing. Okay, so check my algebra if you want. That's fine. Right? But that's where we're at. Right? You guys have any questions right now? Got anything? All right. So Thursday, right? You guys get to stay home. Right? I guess I'll see you guys again on Tuesday. Make sure that if you're coming to class on Thursday, please bring your laptop. Right? There's going to be some group discussion with your groups and breakout rooms. So make sure that you bring your laptops. All right.